Chalk Talk is brought to you by Isolite, the emergency lighting experts. Stay educated, my friends.
To quote Bill Dodds, Labor Day is a glorious holiday because your child will be going back to school the next day. It would have been called Independence Day, but that name was already taken. We hope you get a little chuckle out of that one, and we hope you're looking forward to your Labor Day weekend. I'm Western Regional Sales Manager Greg Keel, along with Eastern Regional Sales Manager Matt Bird. And as you can see, our topic for our Chalk Talk this August is navigating inverter phase options. Typically, you're going to see three-phase or single-phase, but we also offer two and split-phase, and we really wanted to talk about what each phase represents and why you may use one over the other in an application. It's jam-packed today, so as always, our host is our Director of Product Development, Evan Ackman. Evan, thank you for the great quote. Take it away.
You know, I realize that quote almost doesn't work anymore since kids keep going back to school earlier and earlier. Although my kids don't even go back on Tuesday, they go back on Wednesday. So I need one extra day until Independence Day. Thanks for that intro, Greg, and thank you all for joining us. As Greg mentioned, we're going to be talking about inverter systems, really power systems and inverter phasing today. And it's kind of a by popular request kind of presentation. A lot of people have questions on, well, I see on your E3MAC and E3MAX cut sheets that you have 1, 2, 3 split phase options. What the heck does any of that stuff mean? The topic can be a little bit technical, but I think that we've done a good job here getting something for everybody. So we're going to start in this first section by really going back to basics. You've probably all heard of AC versus DC power. We'll just go through and talk about what those two terms mean and some of the ramifications of it. Why AC1 for power distribution systems, but then the limitations that have come up through that. We'll then jump in and talk about three-phase, two-phase, single and split phase systems, where they show up, when you might need to utilize those. Generally, it's going to be something that the engineer has specified, but at least this will make it dangerous on the terminology. And then we'll end by going through a quick product overview. What products are really single phase only? What products have a lot of different phasing options and some notes about that. And we'll leave you at the end with some key points, just a couple sort of reminders that you can look back on to try to help you navigate your way through. Because this is a Chalk Talk, you guys are muted, but of course, as always, we welcome questions. Please throw them in the chat, throw them in the Q&A. We'll make sure we answer all of them before we get off of this presentation here today. So starting with the absolute basics, AC, alternating current versus DC, direct current. We've heard these terms, but I think it's important to understand exactly how they work. And so this will be the drawing portion of the Chalk Talk today. Alternating current does exactly what it sounds like. In one instance, it's going to be driving current this direction, and then at some point, it's going to be driving current back the other direction. This is where we actually get that sine wave that we tend to think of when we think about our power systems that we're dealing with, right? This side right here means that current's flowing in the positive direction. This side means that current is flowing in the negative direction. And for those of you who did your pre-rating, you would know that this is a 60 hertz signal, which we'll talk about. So this happens 60 times every second in power systems, really like the power generation systems. Direct current could also be called like non-alternating current. Really, the current is only going to flow in one direction. And so if we were going to draw that graphically, it would just look like a big straight line at whatever the voltage was. These two things sort of, why you would use one versus the other kind of varies. We use alternating current because it's very easy to generate. Everything that sort of generates power by a spinning magnet inside a coil of wire. So that's everything from renewables like hydroelectric and wind power, nuclear, to the traditional old style coal, natural gas plants where you're just making heat and driving steam through a turbine. That's all alternating current. Direct current is what you're going to see coming out of things like your USB port. So that's how you charge your phone. Things like batteries. If you've replaced the 9-volt battery in your smoke detector recently, that's 9 volts DC. If you haven't done it recently, it's that time of year, so go ahead and do it. But the key of AC and the reason why we use it in power systems is really because of sort of a very technical reason. And that's that changes in currents create magnetic fields, and magnetic fields means that you can you can have things like transformers. And so this is a kind of a simplified example of how a power system would work, right? Power generation. Remember, I said that anything that's going to be a spinning turbine creates AC power. A transformer is a device that allows us to keep a constant amount of power, but trade voltage and current. And so why would you want to do that? More current, generally speaking, needs larger wire. So, if you've wired your house, you might know that a 15 amp circuit only needs 14 gauge cable, whereas a 20 amp circuit needs a 12 gauge piece of wire in there. And that actually goes all the way up. And so if you're going to generate enough power to provide power for an entire neighborhood, if you keep that at a relatively low voltage, that's going to be a crazy high current, which means that the wires would have to be, as thick as a Buick or something. And so a transformer allows this to go, from whatever voltage this system was generated at up to some crazy high number, right? Like maybe 400,000 volts or something, which means we can keep our currents down, which means the wires are very small. And then when we get back to our buildings or our houses, we can go back down to, 277, 240, 480, something significantly lower, and then trade for that current. And that's sort of what we end up with in terms of how our power systems are generated. It also just so happens that AC happens to be a little bit safer. It's also easier to generate things like circuit breakers for. So, generally speaking, the reasons why AC won are numerous, but this transformer thing and power generation means that the entire systems are a lot less costly and easier to manufacture. But that's not without some limitations. I showed you before that AC circuits, they go through the cycle where it goes, positive and then negative and positive and then negative. And it does that 60 times per second, right? And so you're going to see these drawings all over the place. And 60 times per second seems like it's really fast, but in the terms of like electronics and motors in the world of the very small, it's actually ridiculously slow. We think of like electricity being sort of invisible, but you could actually hear 60 hertz. Like if you take a wire and run it next to like a preamplified audio signal, you can actually hear that 60 hertz hum in a subwoofer. And so it's relatively slow. It's like 500 million times slower than the computer you're probably sitting on right now. The net result of that is if you look at this signal, there are periods of time here where there's really no voltage on the line, which means that there's really no power that can be derived from that signal. Excuse me. So, generally, high power motor loads and other loads take big drinks of power at these peaks, and they can't really get any power here. And that really drives down the efficiency. So if you look at sort of how power ends up being delivered to loads, it's really kind of like this, which is very inefficient, and it causes harmonic distortion. It's had all sorts of bad things. And this is the reason why we don't just use single phase, we use multiple phase. Really, three-phase electricity is what is most common in most power generation systems. And really what that looks like is it's just three single-phase systems kind of overlaid in such a way that there's always power available to you. So if you look at this drawing here, right, this blue line mimics the same one that's over here on the left side, but now there are three of them, and they happen to be offset perfectly 1/3 away from each other. The net result of that means is that you always have some power available, no matter where you draw this line, either phase to phase or from phase to this zero mark, which we'll talk about here. You have power that can be delivered. And so when you have these high power, high efficiency loads like HVAC systems, elevator motors, really anything that requires just a lot of power, a three-phase system is going to be the way that gets powered. And that's really how we provide power to our buildings, really to solve those efficiency problems, which leads us into sort of the first discussion on phasing. Now, this is probably it's definitely the most common for commercial installations. It's sort of tied in our inverter offering for what's the most popular, three-phase versus single-phase. But really, almost every commercial building that you see is going to have three-phase 480 power coming in. And the reason why we say it's 480 is that actually makes 277 as well. You can kind of get into the math here. But basically, there's a difference between phase to phase. So, from hot 1 to hot 2. So from this wire down to any of the other 2 wires, versus that phase to neutral. And so you can see that these numbers are actually sort of different when you go and look at it. So that's 480 versus 277. And almost, like I said, almost every building is going to have this at its input. This is going to be what is coming in off of from the power company. If you're providing an inverter that's going to be hooked up to that main breaker panel and then it's going to feed sub panels, it's likely going to be something like a 3-phase inverter system. Similar to 3-phase, but slightly different, is the very strange 2-phase system. You can think of this as a 3-phase system with one of the wires removed. So from this drawing in the upper right, if you remember back to the previous slide, there was this other phase coming off right here, which would give us another output. It's just like removing one of those. It still has the same input and output voltages, but in reality, it only has 2 of them. And so in this situation, some places around the United States, this is fairly common, where there may be a 3-phase power system on the pole, but only 2 are brought to buildings. That's kind of a historical vestige that doesn't really exist in new construction anymore. But where this does come up is if you're going to be directly driving things like 277 volt lights, and not a sub panel, but you have a 3-phase system and you need enough power to drive 2 different phases of it, this is the thing that you would then use in those applications. Again, it's pretty rare. There's a little bit of wiring nuance about how you deal with this and when isolation transformers are required. Generally speaking, 2-phase is the least common of the options that we offer in our large inverters. So if you do see it, maybe take a quick look and just make sure that you're just driving loads, you're not trying to feed a sub panel, and that it's really just done to sort of match and balance loads off of each of the phases of a 3-phase system upstream of it. Split phase is not super common in resident or in commercial systems, but it's how every residential system is actually wired. There is let's not say 100%, but a 99.9% chance this is exactly how your house works. So you might say, well, split phase and 2-phase are kind of the same thing, and they're similar in terms of how they're drawn, but there's a key difference. Remember, in the split phase, we were basically 1/3 of a cycle off on our sine wave. In split phase, we have the characteristic that we're perfectly out of phase. So 1 phase is high, 1 phase is low. The reason for that is that every residential system is a 240 volt system. Most people think that you have a 120 volt system. You do not. You have 240 volts coming in from the power company. That is then sort of split with a center tap so that you get 2 separate phases of 120 for your outlets. And you have this thing that you'll see in your breaker panel where you have like those 2 breakers strapped to each other. That's a 240 volt breaker. You're actually wiring that phase to phase for higher power loads. Again, not super common in commercial spaces, but it does show up in those places where it's like a converted residential and now it's commercial. I think of this as like the dentist's offices of the world. And then single phase systems. You would think that this would be the least common because I told you that every commercial system is probably going to be 3-phase and every residential system is really a split phase. But this can be thought of as like the leaf node solution. And so 120 or 277 volts, this is kind of the last leg between some sub panel and then all of the lights or outlets or whatever devices are being backed up. So this is probably the most common offering in our lineup is the single phase. It's also the most simple to understand, right? Single, some amount of voltage coming in, and that same voltage is going straight out. It is the most simple, and it is the most prevalent in terms of the inverter offering. Now, in terms of the products, you can really sort of drive this into 2 categories. We have the single phase only and the smaller products. That's the E3 Mini, the E3, and the E3X, and it's true also of like the smaller inverters too. But really, these are intended to be out on those leaf nodes, right? Like there is some circuit breaker, it's feeding this area. We want to stuff an inverter in the middle to keep some of those lights on in the emergency. That's going to be those devices on the left. When you go over to the right in the E3MAC and the E3MAX line, that's where we start to get into a little bit more sort of building infrastructure. So it's more likely that we're going to be providing power to sub panels. We're going to be a little bit further upstream in the architecture of the building's power system. And so when you get to the E3MAC and the E3MAX, that's when you're going to be doing things like selecting what type of phasing do you want. Do I want this to be a 3-phase system so that I can basically rip power straight from the main breaker panel and then feed more sub panels downstream? Or do I need single phase because I'm going to basically directly power all of the lights and use my own circuit breakers as the protective devices downstream? So that's really where we start to make those elections all the way up there. And our cut sheets are up to date. It has all the information. But I put this chart in here to just give you an idea of exactly how it works. I'm not going to read the whole thing verbatim, but there's 2 things I want to draw your attention to. First and foremost is this does not match the cut sheets perfectly. This list here is what I would consider kind of the standard offering. If you have one of these options, then you're probably doing the right thing. But that doesn't mean we don't do custom, particularly in things like single phase. We can do higher voltages. We do mixed output voltages sometimes. So there's a little bit more that we're capable of doing, but this is kind of the standard offering. One other thing that I want to just draw your attention to, there's another strange thing that shows up in these tables, and I'm going to circle them right now. And that's in the single phase. At some point in the line around 8,000 watts, we stop offering 120 volt systems, and we only offer 277 and above in terms of the voltage. The reason for that is actually the same thing that we talked about way back at the very beginning of this presentation. And remember that when we trade voltage and current, we like to keep current low because otherwise the conductors get crazy large. That's the same thing here. 120 volt systems at 17,000 watts, that wire would have to be like a 4-gauge wire, which you really can't utilize properly in like a building construction environment. It's not super common, and it really would not be a good fit. So at that point, we really basically double and sum the voltage so that we can keep the current levels a little bit lower. So keep that in mind when you're designing systems, that you can't do crazy high wattages on 120 volt systems. And then last but certainly not least are the key points. So remember that power versus cost efficiency. Generally speaking, to keep the cost down overall for a building, you want to keep the voltages as high as possible for as long as possible. More conductors means more money, basically. And for the same reason that we use transformers to create those big 400,000 volt high power, high tension lines, the same thing applies to these systems, right? 3-phase, lower current, higher voltage systems, they're going to save you money for the entire construction of the building. 3-phase systems are going to be the most common in every commercial space. It's going to be what drives large motors directly, but it's also going to be the thing that's coming in from the building in most cases. 2-phase, pretty rare. Jurisdictionally, it shows up in some places, Philadelphia being one of them, actually. There are also some use cases for trying to be a little bit cute about how you do some phase balancing in 3-phase systems. Generally not particularly useful, but we do sell some. So if you need it, you need it. If you're being asked for it, then we can certainly provide something for you. Split phase systems, much more common in residential, but it does show up in some light commercial or in, let's just call it commercial residential system, like condos and things like that, where there are emergency lighting requirements. And then single phase is your solution all the way out of those leaf nodes. If you're being powered from a branch circuit breaker and you're just trying to keep the lights on, that's generally going to be a single phase system. It's the most common inverter configuration that we offer. With that said, there's a lot of stuff available on the website already. All of our spec sheets are up to date. They have this information. We have wiring diagrams that show a lot of this stuff. Our boilerplate specifications go into a little bit of detail about the voltages that you can get on all of those different options for the inverters. One thing that I didn't put here, because I don't know if it's going to be available when we send out the follow-up, but we are creating a white paper that's going to go into a little bit more detail on this subject. We're just trying to figure out exactly what that looks like and how much detail is appropriate versus just putting together like a 400-page electrical engineering textbook. So look for that too. We'll certainly send out an email, and we're hoping to get it done by the time we send out the follow-up. As always, as a part of this follow-up, we'll send a video of us giving the presentation. You'll have access to these slides so that you can give the presentation yourself or review it when you've got some windshield time. And then any of the sell sheets and marketing assets that we have for the inverters will go out as well. With that said, I'm Evan, Ben, Greg, and Matt are on the line. If there's anything that you guys need support with, please don't hesitate to reach out, whether that's inverter phasing or anything else that we do. We love helping you guys. We recognize that you're out there on the front lines supporting us and fighting the good fight. So anything we can do to make your lives easier, we are 100% in for. I hope you all enjoy your Labor Day. Make sure that you keep it nice, happy, and safe. And we will talk to you again next month. If you have questions, I'll certainly stick around and answer them now.